So for our last bit of basic integration techniques anyway, there will be more advanced integration techniques later, but for our last bit of basic integration techniques, we're going to take a look at integrals that involve inverse trigonometry. And of course, finding an antiderivative is just undifferentiating, so let's start by reminding ourselves of our differentiation rules for inverse trigonometric functions. All right, and of course I know that you know these, just off the top of your head, recite them in your sleep, but let's refresh our memories. All right, the derivative of arcsine of x is, 1 over the square root of 1 minus x squared. And luckily, the derivative of arc cosine x, it's just the opposite of that, right? Adding the to go from arc sine to arc cosine, you just add a negative. So this will be negative 1 over root 1 minus x squared. All right, so now to tangent and cotangent, right? The derivative of arc tan of x would be 1 over 1 plus x squared. And so using the rule that going from tangent to cotangent just adds a negative, that leaves us with negative 1 over 1 plus x squared. And last but not least, the derivative of arc secant will be 1 over, and then the absolute value of x, and then under the radical, x squared minus 1. And so then, of course, the derivative of arc cosecant will just be negative 1 over the absolute value of x times the square root of x squared minus 1. Great. So that's what we know already. All right, and now I want to use these differentiation rules to get at antiderivatives that involve inverse trigonometric functions. All right, so, you have your page in front of you. So you can keep referring to, those differentiation rules as needed. All right, but let's go ahead and differentiate this function f here in part A. And I'm going to be a little bit particular about how I format things. So don't let that trip you up. All right. So the derivative of arcsine blank is, right? And so let's just specify, right? For f prime, we'll have 1 over the square root of 1 minus blank squared. So in this case, that is x squared over 3 all squared. And we just need to keep in mind that we now have a little inner function with its own derivative. So we have to apply chain rule here. So that's going to be times 2x over 3. All right, and then I'm going to begin formatting a little bit differently, so some things jump out at us. I'm just going to pull the 2x over 3 out to the front, sort of get it out of the way. All right, I'm not loving the complex fraction situation here, so let's start, working at that. So I'm actually going to square the stuff that's being squared, so I'll have 1 minus x to the 4th over 9. And then I still have a complex fraction. I don't love that. All right, so let's make it not complex. All right, so just carrying the 2x over 3 down, all right, I will rewrite the 1 as 9 over 9, right, so that I can actually do this subtraction. And let's make sure that's actually subtraction. All right, and then let's get a common denominator. And so we'll have the square root of 9 minus x to the 4th, all over 9. And then I'm going to use a property of radicals, right, that says that the square root of a over b can be rewritten as the square root of a over the square root of b. I can just break them up and give each its own private radical. So I will have the square root of 9 minus x to the 4th over the square root of 9, and then I can simplify the square root of 9, right? That's sort of the point of doing that, is that we can reduce that. So we still have the square root of 9 minus x to the 4th It's a minus. Ooh, it's fighting me on that minus sign, over 3. Okay, and then, right, dividing by this whole fraction here is just going to be the same as multiplying by its reciprocal. So let's show that. So we'll say, right, instead of 1 over all of this stuff, I'm just going to flip it, and I'll say times 3 over the square root of 9 minus x to the 4th, right? And then, right, the 3's cancel out. So that's nice, right? And we're left with 2x over the square root of 9 minus x to the 4th. Yay! All right, so let's see where everything came from, all right, based on the original expression that we were working with, right? So if you look back at the top, we have the x squared over 3. That was the stuff that was in our arcsine function. And notice that each of the pieces that we see in our final expression for f prime is related to what we saw back at the top up here. For example, right, what about this x to the 4th? Where did that come from, right? Well, that x to the 4th was x squared, right? That thing that we saw in the numerator squared. The 9 was the 3 squared. And then what about the 2x that we're seeing up here? Where did that 2x come from? Ah, that was the derivative of this x squared. All right, so we could start to see a pattern here, but that pattern all rests on using, effectively, a u substitution. So if I call x squared u, right, u is obviously a function of x, right, then we can label this 2x right here as the derivative of u with respect to x, right? So that's u prime, or you could say du dx or whatever. All right, so ultimately, let's break this down even a little bit further still, okay? So if I were to now rewrite this in terms of my u variables instead of x's, and don't worry, there's a point to this, all right, up top, instead of the 2x, I'm going to write du, and then over the square root of, all right, instead of 3 could have been any number. It could have been any constant, all right, so we end up using a as a constant. So instead of 3 squared, I'm just going to write a squared, and then minus, instead of x to the 4th, I will write u squared, since u was x squared and we have x squared squared, all right? And notice how that picks up all the pieces, right? So let's see what we can figure out here, right? So this was the final expression that we arrived at when we differentiated. And then we kind of like did the u sub backwards, right? We got the derivative and then switched out x's for u's. So let's see what would happen if we were to integrate this. All right, if we were to throw this into an integral, what would we end up with? Well, we know that we started with an arcsine, right? So this is definitely going to go to arcsine. And then notice what it was. It was x squared over 3. In other words, the thing that we chose for u, and then over 3, oh, that's over a. And then, of course, if we were integrating, we'd have to throw on a plus c. All right, so this should go on the integration rules sheet that you have, that gold sheet, right? We're going to box this up, that the antiderivative of du over root a squared minus u squared will go to arcsine of u over a plus c. And we will put this all into practice very shortly, but I want to at least, prove each of these antiderivatives first. So that will bring us to the next page. Okay, so now in part B, we have a function that is arctan. So if we were going to differentiate, again, you can refer back to your differentiation rules on the previous page, right? But we're going to say f prime, that's a prime, come on, equals, all right, well now we have a 1/5 in front. All right, so that's just going to be a scalar multiple that we keep around. All right, so I'm going to do that in a different color so that we remember. All right, so the 1/5, that's just a scalar multiple. Now let's commence with the arctan part. All right, and the derivative of arctan anything is 1/1 plus that anything squared. So we will do 2x over 5 squared, and then we need chain rule because, right, this expression inside has its own derivative, and really that's like 2/5 times x. So from chain rule, we will get a 2/5. All right, so then, right, times 2/5. Okay, great. All right, so now, again, let's start to clean this up and reformat it so that it looks the way we want it to look. All right, so we're going to keep the 1/5 out in front. Let's actually go ahead and square the 2x over 5. So we'll have 1 plus 4x squared over 25, and then times 2/5. All right. And so now from there, again, complex fraction, not really a fan. All right, so from there, all right, again, just keeping that 1/5 out in front, we'll get a common denominator of 25. So that 1 will become a 25 over 25, and we'll have 25 plus 4x squared over 25, and then still times 2/5 from chain rule. Okay, and so now, instead of 1 over all of this business, right, we can just say the reciprocal of, right, so we'll have 1/5 times 25 over 25 plus 4x squared, that's a plus sign, and then times our 2/5 from chain rule. Alrighty, and then some things are going to cancel. All right, in this case, right, really the 5 here times the 5 here, right, that's going to make a 25, so the 25 will cancel with both of these, and then you'll just be left with on top the 2, the lone 2, right, and then on bottom 25 plus 4x squared, and that's our final answer for f prime. And so now let's break that apart and see where everything came from, all right, in terms of our original expression for f. All right, so again, if we sort of break up the numerator and denominator of the expression inside, right, we look at this 2x here. Whoops. We look at this 2x, and we see that used down here, 4x squared, that's 2x squared. So 2x is sort of acting like our u, right? Then this 25, oh, well that came from our denominator down here, right? This was 5 squared. So the 5 is kind of going to act like our a, right? Our constant. And then the 2 up here, right? Where did this 2 in red come from? Well, if we sort of trace our steps backwards through our algebra, we see that that 2 came from our chain rule, the derivative of our inside function. But really, you can also match it up to our expression for u, to this guy right here, right? 2 is the derivative of u with respect to x, right? So this is our u prime. Okay, so let's throw this into an integral and see if we can rewrite this in terms of u's instead of x's and get a general expression. All right, so if we put this into an integral, we had, right, u prime, right, or we'll say du. It's really du dx, but it'll cancel. More on that in a moment. All right, so du over, now instead of 25, that was 5 squared, but we're calling 5a, so a squared, and then plus, not 2x squared, but u squared, right? And so then we know that if we integrate that expression, all right, well now let's see what we get. The 1/5. Oh, that's 1 over 5, which is 1 over a arctan, and then we have function u on top, and then a in the bottom. And then, of course, we'll throw in a plus c. Okay, great. So that's another one to put on your integration rules sheet. All right. And then this last example, all right, down here, I'm actually going to change it. I don't like it as much because it just so happens, it's just like a coincidence that the function I picked, things end up canceling that like I didn't want to cancel. It's not so easy to see. So I'm going to change this one for part C pretty much completely. All right, so actually for part C, what I want to start with, I want to now do this like in completely general terms because we sort of see this pattern here, right? We end up with like a 1 over a, and then in arcsecant of some function u over a, that seems to be the format that we're working with, right? So let's just go ahead and get f prime from here. All right, so now we have to remember that a is constant. In fact, let's make a note of that up here, right? A is constant. Okay, and then u is a function of x. Okay. All right, so f prime, right, well, the 1 over a, it's just going to hang around like a constant. And now the derivative of arcsecant is, right, we'll have 1 over the stuff inside the arcsecant function. So 1 over the absolute value of u over a, right, and then times the radical of u over a squared minus 1. And then now we know that u is a function of x, right? So we need some chain rule happening in here, right? And so the derivative of u over a will be whatever u prime is over a, right? Because again, a is just a constant. Oh, come on. There we go. Alrighty. My handwriting is so messy on this. I apologize. All right, but now let's start to clean things up. Alrighty, so we've got 1 over a, and then let's start chipping away at this complex fraction down here. So I will leave the absolute value of u over a. All right, and then I'll actually square the stuff that's in the radical. So I'll have u squared over a squared minus 1, and then we'll still have u prime over a. Okay, and our procedure is going to be the same. We're going to go get a common denominator, all right, in this fraction down here. So u over a, and then we'll have radical, well, the common denominator for the expression in our radical is a squared. So instead of writing 1 as 1, we will write 1 as a squared over a squared so that we can write u squared minus a squared all over a squared. And then we still have a u prime over a. All right, and then the whole point of getting to one single fraction under the radical is to use this trick, right, that lets us separate the numerator and denominator of a radical like this. So we've still got u prime over a. And then that allows us to say 1 over the absolute value of u over a. And then we still have the square root of u squared minus a squared. Come on, minus signs. And then the square root of a squared is a. Yay. All right, we're coming on home. All right, so let's figure this out. All right. All right, let's clean this up. All right, again, this middle fraction here, let's take its reciprocal, right? Instead of dividing by this whole big, terrible fraction, let's multiply by its reciprocal. So really, we will have times the absolute value of a over u, and then a over the square root of u squared minus a squared times u prime over a. All right, and now some things are going to cancel. All right, and you're going to have to kind of let me fudge the absolute value on one of these pieces. You're basically going to have to let me do this. That's a times, not a minus. So the absolute value of a over the absolute value of u, right? That's a property of absolute value. We are totally allowed to do that. But you'll see where the sort of fudgy part comes in here. I'm going to say that in this case, a is positive, all right, so that we can sort of drop these brackets here. And it would have to be, that comes out of properties of arcsecant, all right. So really now what we have is a times a on top and a times a on bottom, so these are going to cancel. And you end up with u prime over the absolute value of u times u squared minus a squared. So the nice thing is, if we see something in this format as our integrand, we know what it will integrate to, right? Something of this format integrates to 1 over a times the arcsecant of u over a. But let's just, write that in there for sure. All right, so if we were to integrate something of the format du over the absolute value of u times u squared minus a squared, right, that actually goes to 1 over a times arcsecant. And then this is something that we're going to have to add in. We have to add in the absolute value of u over a, okay? And then, of course, all plus c. Again, that just has to do with the domain of arcsecant, right? We can only have a positive number in there because of domain restrictions, all right? So here's the last one for your blue sheet, and you will note something. We only have 3. Right? Why do we only have antiderivatives for 3 of our inverse trigonometric functions? Well, if we know, for example, that the antiderivative of, let's see, du over 1 plus, let's undo that. I should be saying a squared plus u squared. Right, that's going to go to 1 over a arctan u over a plus c. But remember, the derivatives of arctan and arccotan were just off by a negative. So something that would integrate to arccotangent would look like this. Negative du over a squared plus u squared. So we could say that that's going to go to 1 over a arc cotangent u over a plus c, or we could just say that that's negative 1 over a arctan u over a. So since they're and then of course plus c, but I'm out of room here. All right, so we could do all 6, but it's really only worth memorizing 3 because you could just say that, right, if you're just off by a negative, right, you can just pull this outside and then treat it like an arctan. All right, so hey, they're a little bit complicated, but at least there's 3 and not 6. All right, so now let's get to the examples. All right, again, fundamentally, this is all just one big sort of specialized U substitution, I guess you could say. But then, of course, as always, we need to talk about a couple nitpicky things that will come up. All right, on to the next page. All right, so I think in this box, I wanted us to put all of our antiderivatives. All right, so in here, I want you to put the 3 big ones. All right, I want you to put that the antiderivative of something of this format, right, the square root of a squared minus u squared will go to arc sine u over a plus c. Something of this format, right, the antiderivative of a squared plus u squared, right, in the denominator, will go to 1 over a times arctan of u over a plus c. And then, last but not least, the antiderivative of something of this format, right, u squared minus a squared, will go to 1 over a arc secant, and then absolute value of u over a, but all of it on the inside, right? Okay, and so then sort of a nice way to think about it is that as we go from arcsine to arctan, we add one thing, right? Going from arcsine to arctan, we add the 1 over a in front, and then going from arctan to arcsecant, we just add the absolute value brackets, right? So it's just sort of like with each one that we proved, we just add an additional component, right? But fundamentally, their structure is all the same. All right, so let's take a look. All right, so we see the radicals, we see things that look like they're being squared, so we're like, hey, this looks like it could go to some inverse trig. All right, so the first thing is to set up a u sub effectively and to identify, right, what's your function that's being squared, what's your u, and then what's your constant that's being squared, all right? Right, if we look back up here, right, what's our u, what's our a? And just looking at this format right here, which of the 3 inverse trigonometric functions does it look like we're dealing with? Well, there's a radical, so it's probably arcsine or arcsecant, right? But there's no absolute value term in front of the radical, so it's probably an arcsine. So that's what we're going for. They will not always go as planned, but you start anyway and you see what happens. Okay? So here, let's choose u and a. Here, our function, right, we can say that this is u squared, so this would mean that u is 5x, right? 25x squared is 5x squared, so that tells us that u is 5x, okay? And then here, 16 is 4 squared, so that tells us that a is 4. Great. So let's start to rewrite. Okay. So we're still going to do all the things that we do when we're doing a u sub. It's no different. All right. And with that, we realize we have missed a step, right? Usually when we do a u sub, we go ahead and get du dx. So let's do that, right? Let's do that right from here. So here, du dx would be 5. Okay, great. Right, don't really know where that's going to come in, but it will, right? All right, so let's start to rewrite. We have our integral. we have dx. I don't know if I want to rewrite that yet, but we'll see. So let's take care of the bottom first. All right, we obviously have the square root, whoops, of a squared minus u squared, okay? And now, so by writing, all right, I took care of this, I took care of the radical, I took care of the 16 minus 25x squared. All right, so now I need something that is exactly equivalent to dx. All right, and that will come from here with algebra. All right, so dx, right, if we cross multiply, right, we get that du equals 5dx. Therefore, dx equals du over 5. So by writing du over 5, I will have taken care of the dx. So I'm just going to put a 1 up top here and write du over 5, which takes care of that. Great. And now we've got this like over 5 thing happening, but whatever. That's just a constant multiple of 1/5 out in front of the integral. And then we have this like textbook arcsine integral, right? Right, look at the integral that we've written here. Look back up at arcsine. Again, it's not pretty up there. My handwriting on this is abysmal, but that's what it is. And so it's going to integrate to arcsine u over a plus c. So let's do that. This integrates to, again, 1/5 arcsine, and then u over a plus c, but of course we'll want to back substitute. We don't want to leave it as u's and a's. That was just a trick, right, to help us get through the problem. So in this case, let's look back at our definitions. U was 5x, and a was 4 plus c. Done. All right. Let's see. What do we got here? Yeah, you know, let's go through all of these. All right, example 2. So same thing. All right, if we look at what we have in the integrand, we've got, okay, I don't see a radical, right? But I see things being squared, right? I don't see a function derivative pattern, like that would maybe clue me into natural log or something, right? If I look at the bottom, the derivative of the bottom would be 18x, you know, which is of the order x to the first, right? And I don't see anything, you know, with an x in the numerator, so I don't think it's going to go to a natural log. And that's the toughest part, is when you have all of these types of integrals mixed up together and you have to pick out what the appropriate technique is. But that's something that we'll do together more extensively in class. So for now, right, we're pretty sure this is going to go to an arctan. All right, so let's do that. All right, here it looks like our little function that's being squared, right? 9x squared, that's the quantity 3x squared. So that tells me that the function being squared, u, is 3x. And now it looks like 2 is my a squared. All right, so if 2 is a squared, then what is a? Well, then in that case, a is root 2. Yay. Right? That's easy. It's a number. It works. All right, so now let's start rewriting our integral, but let's not forget the step that we always need to do with a u sub, right? We have u, but let's go get du dx, because eventually we're going to need to replace a dx with a du that's equivalent. All right, so du dx is 3. All right, so now, all right, let's do our integral. I'm going to save my dx, all right, but 2, instead of writing 2, I will write a squared. Instead of writing 9x squared, I will write u squared. And then dx, well, with a little bit of algebra over here, you'll find that dx is exactly equal to du over 3. So I'll just put a placeholder 1 there, and then a du over 3. And again, the over 3 I don't worry about because it just comes out front as a scalar multiple. and then this is textbook arctan, right? You have 1/3 times, now here's the tricky part, the 1/3 was the scalar multiple, but the antiderivative of arctan itself includes a 1/a in front as well, right? So don't let the fact that you already have a 1/3 out there let you neglect that 1/a that we need to include. All right, and then from there, we now back substitute. That's 1/3. A was √2. Arctan, and then u over a. I know that looks like u over u. It is not. It is u over a. So u is 3x, and a is √2 plus c, right? And we could clean this up, right? We could just sort of condense this into one fraction, but that is not the point of this exercise, and do not worry about rationalizing this. Obviously, we do not care about radicals in the denominator. All right, not too bad. All right, and the next two examples I really like because they are similar and yet different. All right, so I might try example 3 2 ways and see what happens. Well, yeah, let's just see what happens. Let's start saying, you know what? I think that this, based on what I see, it looks like an arc sign, right? I see a radical, right? But no absolute value thing hanging out in front of it. So it's looking like an arc sign. All right, so let's see what happens. Alrighty. So actually, this couldn't be an arc sign. Well, at least not right now, because arc sign is a squared minus u squared, and this looks like it would be of the format u squared minus a squared. So something's off. All right, but again, let's just try it. All right, if we were going to do this, this would be my u, or u squared, right? In this case, u squared would be e to the 2x. So this is really e to the x squared. So that would tell me that u is e to the x. And then here, a squared is 1, right? So that tells me that a is also 1. Okay, so now let's start to rewrite our integral. All right, I'm going to give myself some space to find my du dx here before I do that. So let's see, du dx is e to the x. Cool. All right. So if we start to rewrite, all right, e to the 2x. I don't know what that is right now, so we'll leave that. All right, let's put in our radical. And then e to the 2x, that we are going to call u squared. And then minus 1, oh, that will be a squared. Now we've got some stuff that we need to do. Alrighty. E to the 2x, technically that's also u squared, right? If u is e to the x, u squared is e to the x squared, which is e to the 2x. So I could write u squared up here, and then dx would be du over e to the x, which is, e to the x is actually just u, right? This is just u. So this would cancel, and we'd be left with u du over u squared minus a squared. And that is not, that's not arc sign. It's not arc anything. And so actually the trick with this is that it is not going to go to inverse trig at all, right? We missed a function derivative pattern early on. All right, so let's draw a line and try this again. All right, the first question we should always ask ourselves is, do I see a function somewhere and its derivative somewhere else? Because that's like a basic u substitution, right? And the answer here is yes, right? This e to the 2x on top is the derivative of the e to the 2x in the bottom, right? So we could actually say that u is e to the 2x, and then there's no reason not to include the minus 1 with that as well, right? So now du dx, right, would be the derivative of e to the 2x minus 1, which is 2 e to the 2x. Okay, so now let's start to rewrite. Okay, let's rewrite our integral. All right, and I'm going to save the numerator. So now instead of the square root of e to the 2x minus 1, I can just write the square root of u. All right, I need something. I could either handle each of these separately. This is all done. Or I could look for something that is equivalent to e to the 2x dx. That's what I'm going to do. I'm lazy, right? So from here, if I multiply both sides by dx, I get du is equal to 2e to the 2x times dx. Therefore, du over 2 is exactly equal to e to the 2x dx. So let's write that in. All right, du over 2. And that takes care of all of that in one step. You could do it in 2, though. So I'll pull the 1/2 out as the scalar multiple. And then I'm going to remember, now this is not natural log, right? I don't have du over u. I have du over root u. So what I really have is u to the negative 1/2 du. And that's just power rule, right? So that's just going to be, all right, 1/2 u to the positive 1/2 divided by 1/2, so times 2 over 1 plus c, right, which will ultimately just be u to the 1/2 plus c. And when we back substitute, right, well, u to the 1/2, that's just the square root of u, so it's just going to be the square root of u, which is e to the 2x minus 1 plus c. So this wasn't an inverse trig at all. It was just a radical, right? So sometimes it's a little tough to tease apart, and you'll get better at discerning that. All right, but now let's go to example 4, which looks similar, but notice that we don't see that function derivative pattern, right? I don't see a function like e to the 2x, and then its derivative hanging around somewhere. I just see the e to the 2x. So this is probably going to be our inverse trig, but notice, we still have a problem, right? The order's wrong. This is u squared minus a squared. So I don't know that it could be arc sine, but again, right, a lot of students here will just stop and say, oh no, well, it's not an arc sine, it's definitely not an arctan, and it doesn't look like an arcsecant, so I don't know, I can't do it. Well, just go ahead. Try it. You could either try a regular u sub, looking for a function derivative pattern, or you could just go ahead and try an inverse trig. Let's see what happens. All right, so if we were going to do inverse trig from this term, right, we would have that u is e to the x, right, because we have u squared there. And from here, we would gather that a is 1. All right, and here, du dx is, well, e to the x. Fantastic. So let's start to rewrite. All right, I will start by, in the bottom, writing the square root of u squared minus a squared, right? We know, I mean, technically we could write u squared minus a, but we know it has to be u squared minus a squared to fit the format that we want, so fine. All right, and so that takes care of this, the entire denominator. Okay, now I need something that's exactly equal to dx. And look at this, look what happens here, right? Something that's exactly equal to dx is du over e to the x. So let's write that. I'll just put a 1 as a placeholder, du over e to the x. All right, and that takes care of the dx. But notice, I've got u's and x's in my expression still. I don't want that. But if you look back at our top definitions, e to the x is u. So instead, I'll just write u. And now look what we have. The antiderivative of du over, I'm just going to move this u out in front here, u times u squared minus a squared. Oh, look at that. That's an arcsecant, right? So it didn't initially look like it, but when we just began the process, the math kind of worked it out for us, all right? So don't be afraid to just get started. All right, we know that that's going to go to 1 over a arcsecant absolute value of u over a plus c. So now let's back substitute, okay? We'll have 1 over, well, 1 arcsecant, the absolute value of u, which was e to the x, over a, which is 1, plus c. And then there's a number of things that we can do to make this simpler, right? We don't need the 1 over 1. We can just write arcsecant. And we can even drop the absolute value brackets because e to the x is always non-negative. In fact, it's always positive. And there we go. Done. Probably put that in parentheses just for clarity. All right? Not too bad. All right, and so that's the general tone of things. It's sort of figuring out, do I think I have an inverse trig integral, and then choosing u and a appropriately. And if it doesn't work out, maybe just trying a regular old u sub. Okay, you might have to try more than one thing. Remember, we get differentiation rules and we get integration techniques. And then on the next couple pages, we're going to talk about weird stuff that can happen. Okay, hooray. So, as you can see in part 3, sometimes we're going to have to complete the square. All right, I'm not going to do a huge review on completing the square, but I'll obviously talk you through it. If you need additional help on that, I recommend that you, seek some resources online or go to a friend or something. But let's at least first start looking at why we might need to complete the square. All right, so here's the thing. All right, this integral, it looks like a hot mess. It's actually not that bad. But notice, so first of all, we don't see the function derivative pattern. Not the way that we want it, right? Because we would need like a derivative on top, and we maybe see a derivative on bottom, but that doesn't help us. All right, and we see the radical, we see something in front of it, so we're like, oh, maybe it could be an arcsecant, but notice, for arcsecant, we're looking for something of the format du over u times, right, u squared minus a squared. And we don't have that here. We have two functions of x, right? Not some function of x squared minus some constant squared. So basically what that means is we need to find a way to turn this expression into a difference of squares, right? And what will let us do that? Completing the square. All right, so let's begin. All right, I'm really just going to focus on the expression under the radical for now. All right, I'm just going to worry about the x squared minus 2x. All right, so if you remember, when we complete the square, all right, we group the first two terms together. In this case, there are only two terms. All right, so, okay, fine. We group these two terms together, but I'm going to leave a placeholder for a third term. Okay? All right, because we're going to think about something to put here. We're actually not going to think about it. We're going to calculate it. And the way that we calculate what goes there, all right, is that we take half of our b term, our middle term, and square it. All right, so half of -2 is -1, and then we square it, right? So here, really, we did 1/2 of -2, all right, and then we square it, which equals 1. So here we put a plus 1. But we can't just add 1, right? We can't just like put numbers in, right? So we just make sure that we balance it on the outside. And so we're like, oh, I added 1 in here? Well, then let me just strategically subtract 1 out there. All right, and ultimately, this expression that I have up here in blue is equivalent, right, to the circled expression under the radical in red, right? If you simplify it, it's the same thing. All right, but this is just going to be more convenient for us because we can write the expression in parentheses as, right, x minus 1 squared, and then minus 1. So again, this expression in blue, still equivalent to the thing circled in red, but it's now at least something that's of the format some function of x squared minus some constant squared. All right, so that's how completing the square can help us with these inverse trig integrals. Alrighty, so I'm going to first rewrite my integral with my new expression that I created by completing the square. So now under the radical, I have the quantity x minus 1 squared minus 1. And so now let's go ahead and do our u sub. All right, so here it looks like the function being squared is x minus 1, right? And then the constant being squared is 1. Okay, so from there, I will have, all right, rewriting. All right, worry about the top later. All right, this x minus 1, oh, that's u. And then instead of writing x minus 1 squared, I'll just write u squared minus a squared. And then dx. Ah, yes, we need to go get du dx. And du dx is just 1, and that's convenient because that tells me that du is equal to dx. So instead of writing dx, I can literally just write du. Yay. All right, and then this goes right to our arcsecant. 1 over a, arcsecant, absolute value of u over a plus c, and then we back substitute. And so we have 1 over 1, arcsecant, and let's see, u was x minus 1 over a plus c, and then you could clean that up, you know, just to make it a little bit more visually appealing. Okay, on to the next example. Oh, look, a definite integral. Doesn't this look fun? Alrighty, so again, right, I don't see a function derivative pattern here. My bottom is 3x minus x squared under a radical. If I called that u, I don't see a du hanging out anywhere else. So we're like, maybe it's inverse trig. But again, I don't see anything that's like a difference of squares, either u squared minus a squared or a squared minus u squared, right? So let's try, okay? Let's turn this into a difference of squares by completing the square. All right, so let's focus on just the stuff under the radical here, right? So 3x minus x squared. All right, things to note about completing the square, or I should say things to remember. We need to be in the right order, right? We need to be in descending powers of x. So really, we need negative x squared plus 3x, all right? And then the second thing to note is that the coefficient of your x squared term must be 1. So if you have anything other than 1 in front of that x squared, you have to factor it out, whether it's a 3, a 7, a negative 82. In this case, it's just a negative 1, so we have to factor it out. So we have to say negative x squared minus 3x. Leave a blank spot for a placeholder, and let's calculate what goes in that blank spot. It's going to be 1/2 of negative 3 squared. Sorry, all my negatives look like multiplication dots. All right, so half of negative 3, is negative 3/2, and then when we square that, we will get 9/4. The negative, hint, hint, doesn't matter because you always end up squaring it. So let's put plus 9/4. Now, again, we can't just put that there. We need to balance it. All right, but we also need to think, right? It looks like a positive 9/4 in there, but ultimately the negative on the outside gets distributed. So really, we have decreased the value of this expression by 9/4. So we need to add 9/4 back in. I know, feels weird. All right, but then all of that so that we can do this. All right, this expression in parentheses can be rewritten as a trinomial square, right, which would be x minus, is that going to be 3/2? Yeah, x minus 3/2 squared plus 9/4. And you might be saying, oh no, it's not a difference of squares. We wanted a difference of squares, right? Because it's always u squared minus a squared or a squared minus u squared. And well, it actually is if we just reorder our terms. So no big deal. All right, great. So let's rewrite our integral, okay, with our new format. All right, so here, this will be 9/4 and 3/2 down here, and then we'll have dx over the square root of 9/4 minus the quantity. And that, I'm sorry, that shouldn't be x squared there, right? That's just going to be plain old x. My apologies. X minus 3/2 squared. Great. And now we're ready to go with our u sub for inverse trig. All right, so obviously this is a constant, right? This is a squared, right? So if 9/4 is a squared, I then know that a is 3/2. And from here, my function u that's being squared is x minus 3/2. All right, and I'm just going to go ahead right now and get du dx. Du dx is 1. That's nice. And I am going to change my limits of integration to u values. So when x is 3/2, right, I want to change these guys to u values so that I don't have to back substitute. You can though. All right, so when x is 3/2, right, I'm looking here, of course. When x is 3/2, u is 0. All right, and when x is 9/4, well, let's see, u will be 9/4 minus 3/2, so 9/4 minus 6/4, which is 3/4. So if I were to rewrite this, my lower bound in terms of u is now 0, and my upper bound is 3/4. Okay, so that takes care of this. And then in my denominator, I have a squared minus u squared. And then from here, I can see that du and dx must be exactly equal, so I can replace this with du. Great. All right, and we know that this just goes right to plain old arcsine. So this is going to be arcsine of u over a plus c. All right, and then of course we'll still need to do the definite integral part. Let me see if I have any room over here. Oh yeah, okay. Right, so evaluated from u equals 0 to u equals 3/4. And I will back substitute for a because it's a constant, but I'm not going to do it for u. And u has a bunch of fractions, right? So this will be the arcsine of u over, let's see, a was 3/2. So instead of divided by 3/2, let's do times 2/3. And we don't need the c because it's a definite integral, right? So evaluated from 0 to 3/4. All right, and now let's do that definite integral step. all right, we'll have the arc sine of, let's see, first we'll plug in 3/4, so that will be, whoops, I'm going to go back to my pencil here. The arc sine of, let's see, 3/4 times 2/3, right? Well, 3/4 times 2/3 is 2/4, which is 1/2. So arc sine of 1/2 minus, and then we'll plug in our lower limit, arc sine of 0. Arc sine of 1/2, let's see, whose sine is 1/2? That should be pi/6. And whose sine is 0? That's 0. So that should be pi/6. Done. And I believe that's the last example on this page. Good. All right, so long story short, sometimes you got to complete the square. Think about it. All right, on to the last page. We're almost there. All right, this is like the ultimate, like, last resort technique. It's not that bad. It's just, it's just a little bit labor intensive. All right, and it's just something that you want to remember that you can do. All right, and this technique is actually useful for other types of integration as well. It is not just applicable to inverse trig integrals, so it's a handy technique to have under your belt. And so, long story short, what would happen here, if you tried a regular plain old u sub, it would not work out. You wouldn't be able to get everything just in terms of u's nice and cleanly, or really at all. All right, if you tried this as an inverse trig integral, it wouldn't work out either. You'd still have some parts that wouldn't fit in. I think about it like you'd still have like clothes sticking out of your suitcase, and you're trying to push them all into the suitcase and close the suitcase, but you can't. And if we were in class together, I'd have you do it. I'd have you try. So I recommend that you try. See that neither option is really going to work. And now I sort of want to cut to the chase because this is a longer video. All right, that when that happens, you have an option. And if you were to try this on your own, you would see that the thing that is messing us up is the fact that the numerator is a binomial in this case. All right. And again, if you were to just, spend 2 minutes trying this on your own, you would be like, if the numerator were just like a plain old x or a plain old 2, I could totally do this, right? But since it's x plus 2 altogether, it's not going to work out, right? Addition and subtraction, they ruin everything in math, right? And so basically, we do something that eliminates that problem, and it is this, all right? Effectively, we split a sum in the numerator of a fraction into the sum of two separate fractions. So we rewrite the integral like this. X over our entire denominator. Oops. And then plus 2 over our entire denominator. Okay? Right? We're allowed to do that, right? We can say that 3 plus 1 over 5 is 3 over 5 plus 1 over 5, right? So now we basically handle each of these integrals separately. And it turns out that our first integral will not be inverse trig because I see the function derivative pattern, right? I have an x squared on bottom and its derivative roughly on top. So the first integral will be just a regular u sub, okay? So since it's just a regular u sub, I might as well just let u equal my entire expression under the radical, right? Always lump in a constant if you can. All right, so if u is 4 minus x squared, then du dx is negative 2x, okay? And so then, from here, let's start to rewrite. All right, let's see, well, we'll have our integral. And then under our radical, we'll have root u. All right, and so that takes care of this. And then from here, I'm going to get something that's exactly equal to x dx. So let's see, from here, that would be du over negative 2 will equal x dx. So I'll put a 1 here, and I will write du over negative 2. And then we'll proceed from there. So I'll pull out a negative 1/2. And then that does not leave us with, right, it's not going to go to a natural log. We have du over root u, which is really u to the negative 1/2 du. And that's just power rule. All right, so that's negative 1/2. And then reverse power rule, that'll become u to the positive 1/2 divided by 1/2, so times 2 over 1. All right, and then, plus c, of course, which will leave us with a negative u to the 1/2, so negative root u plus c, which is negative root 4 minus x squared. Okay, so let's hang on to that, all right, because that is just 1/2 of our integral. And that's the only reason that this is tough is because, well, now you got to do 2 integrals, and they're different. All right, so now, all right, in the second one, I am probably going to pull that 2 out in front first, but we'll see. All right, so now here, yeah, actually, if I take this and I pull this 2 out in front and put it here, this is definitely an arc sine, right? And you can go ahead and do the whole process, right? But here we can clearly see that u is just x and a is 2, all right? And you might be able to see this pretty easily, right? Really, we're just going to have 2 times, right? In this case, du dx is 1, so du and dx are equal. And then you're going to have root a squared minus u squared, but you could probably even skip this at this point, or if you're feeling comfortable with it. So that's going to be 2 arc sine u over a, right? I'll write it, sure. U over a plus c. And then, of course, we'll put everything back in terms of x's, right? So u, in this case, was just x. A was 2 plus c. And so now these are the 2 pieces that we need to sum together because originally, right, it was this integral plus that integral. So our final answer will be negative root 4 x squared, and then I'll say plus 2 arc sine x over 2, and then just one big plus c, right? Because this c plus our other plus c, that's just some other third constant c. All right, so again, it's not difficult, it's just a lot of work because you have to do 2 integrals. All right, so this last one, I am going to spare you more of me yammering on, but I would challenge you to do 2 things. Firstly, confirm that a regular u substitution will not work. Secondly, confirm that a regular inverse trigonometric u sub won't work. And then finally, split up the fraction, right? Rewrite this integrand as, right, the integral of 4x over root 1 minus x squared plus 3 over root 1 minus x squared dx, and then create 2 separate integrals and handle them each individually. Usually, what's going to end up happening is that one of them will end up being like an inverse trig and the other will not. Right, in this case, for this first one, I see a function derivative pattern, right? I have an x squared on the bottom, and its derivative on top, right? So this is just going to be a regular u sub. And then here, right, again, you can bring the 3 out in front, and then you're like, oh, hey, look, it looks like a regular, you know, probably an arc sine. So this is going to go to inverse trig. All right, so give it a shot. Confirm that you can do it. All right, this might even be an example from your textbook. I'm not sure, so you could check that out. But then after you get through this, it'll be time to hit the suggested exercises. But that concludes all of the basic integration techniques and strategies that you're going to get for now. Congratulations.